Hey, here we go. So, we are going to a brief reasoning. This is not a full. This is not a full proof, everybody. This is not a full proof. Okay. All right. But try to follow it and see if you can connect it. Okay. So we'll end up seeing the shortcut, why it works. We'll call the function y equals a of x. And what we're going to do, we're going to bound it here at 0. And then we're going to bound it here at x. And we're going to call that the area, specifically from 0 to x. Now, I'm going to look at another area. I'm going to look at that area, the red area. And the red area is going to be called area from 0 to x plus h. Here's the question, everybody. This is the key to make it all work together. We have this green area in the middle. We will call it the area from x to x plus h. Tell me, how can we find the area from x to x plus h using the other two? Yeah, find both the areas and subtract them. Very good. So we'll say the area from x to x plus h is going to be equal to the larger area, area from 0 to x plus h, minus area from 0 to x. Everybody okay with that? All right. Now, instead of writing this green area, the area from x to x plus h, I'm going to write it as an approximate area. In order to write an approximate area, let's suppose it was like a rectangle. What would be the width of that rectangle right there? H. Very good. So I'm going to rewrite this to be approximately h times, and then you would have to find the height, right? And the height would be the same as that function, a of x, right? So h times a of x would then be equal to what we said, our area from 0 to x plus h minus the area from 0 to x. Oh boy. Now watch. I'm going to pull a trick here, everybody. I'm going to divide through by h. The function then, a of x, the top function, is equal to a from 0 to x plus h minus a from 0 to x all over h. Whoa! Do you notice something? It looks like a derivative, doesn't it? Look at this. Remember? Hey, remember this? F of, yep. This is the whole point. This is what you want to watch. This is the function of x plus h minus the function of x, all divided by h. What's the only thing we would need to be able to write it as a derivative? The limit as h approaches 0, okay? All right? And the limit as h approaches 0, okay, we'll end up with really just our function height. So what we have here is a of x is equal to the limit h approaches 0 What that means is this. If we take the derivative of the area function, we get that top function. If we take the derivative of the area function, we get the top function. Well, we don't know the area function. What we had to do is we had to use the limit of Riemann sums. Add up an infinite number of rectangles. So let's write this differently. Instead of saying if you take the derivative of the area function to get the top function, we'll write like this. You take the antiderivative of the top function to get the area function. That's what we're doing today. All right. So this is not a full proof by any means. This is a kind of a deductive reasoning to help us understand. If you want to see the proof, you're going to have to look it up. Okay. But this leads us to, we're already in semester 2, and this is the first time we learned the fundamental theorem of calculus. There's 2 parts to it. We're not going to do the first part today. The first part is confusing to a lot of people. We will learn the first part tomorrow. Okay. Today, we're going to talk about the second part. In order to do the second part, you have to understand what antiderivative is. An antiderivative, for example, okay, if you say that f of x is equal to 3x squared, we would say big F of x would be the antiderivative, whereas we'll just list it. What's f prime of x? 6x. We do large F to go the other way. What would you take the derivative of in order to get 3x squared? X to the third. And so there's all sorts of ways now that you could think about finding an antiderivative. People get generally confused, but the rule of thumb is this. Antiderivative for f of x equals x to the n. F of x, large F of x, the antiderivative, would be equal to, we take the exponent and we add 1 and we divide it by that new exponent. So that's your power rule for an antiderivative. Question? Very good. Very good. So it's not important because whatever constant would, they'll subtract off in the end, and I'll show you why. But when we do what we call indefinite integrals later on, we'll get to that constant piece. So let's flip it over to the back side, and let's just do a couple examples, okay? find an antiderivative for the following. So, anybody know what the antiderivative for x to the third is? Very good. X to the fourth over 4. Now, it says and because we used to say find the derivative because there was only one. Now we're saying find an antiderivative because I want you to know that you could also use f of x is equal to x to the fourth over 4 plus 18. I mean, if you take the derivative of that, the constant goes away, right? You still end up with x to the third. So there's an infinite number of antiderivatives for each function. However, this is the simplest one, so to speak. So 5x to the fourth would be x to the fifth. This would be 5x to the fifth over 5, which would just be x to the fifth. This one, 4x to the seventh over 7. Now, do I just increase that 3 to 4? No, so we're back to square one where you have to write it so that it's in power form. So that's 3 over 2 x to the negative third. So let's write it like that. We add 1, so we get f of x is equal to, add 1 and you get negative 2. So we have 3 over 2x to the negative 2. And then you could either write it over negative 2 or multiplied by negative 1/2, however you want to do it. I don't care. So it looks like on the top we get negative 3, and on the bottom we have 4, and we have x squared then as we drop the exponent down. So let's put this into the classic piece. The fundamental theorem of calculus part 2 is the part that's most well known by people, and that's the easiest part to work with. Part 1's a little bit more difficult, but part 2 says this, okay? The integral from a to b of f of x dx. You want to be able to evaluate that. Okay, you want to know what that comes out to. It's equal to simply f of b minus f of a, where f is an antiderivative of f. So, just so we're all clear, what is f of x in problem A? We'll evaluate these. F of x is x squared. So therefore, large f of x is x to the third over 3. So, here's how we actually write it, everybody. Here's the work and the notation that you will show. We will say the integral from 0 to 2. So this is a definite integral. Definite meaning it's bounded, top and bottom. The definite integral of x squared dx, which also refers to the area between 0 and 2 and the x-axis and the function x squared. Okay, I'll draw a little graph here. So the definite integral, referring to that area, is equal to, just want to make sure we all connect the learning here, is equal to, I take the antiderivative, which we've already said is x to the third over 3, and we evaluate it at 2 and at 0, and we subtract the second from the first, okay? So I plug in 2, what's 2 to the third? 8. over 3 minus 0 over 3 is 8/3. No more infinite number of rectangles. So I plugged in 2 and I got 8/3 minus 0. Because it says, the fundamental theorem says you have to do f of b minus f of a. Question. Only because it was x squared. So that's why it came out as thirds, where if it was x to the third, it would be over 4. If it was x to the fifth, it would be over 6. Okay, so that's the reasoning that we're going through. Okay. So let's do another one. 3x squared bounded between 4 and 2. First of all, what is the antiderivative of 3x squared? 3x cubed over 3, or x cubed. Okay. That's all right. And we're going to evaluate that from 2 to 4. So, what is 4 to the third? 64. What's 2 to the third? 'Isn't it cool? No, again, you guys, I'm pretty convinced, okay? I'm pretty convinced that if you gave me the evening, I could teach Kira to do the same thing as she's in 3rd grade. That's not calculus. That's algebra. Okay? All right. Let's try a more difficult one, okay? 3 roots of x. If f of x is equal to 3x to the 1/2, what is large f of x? 3x to the 3/2 divided by 3/2, right? We raise the exponent 1, and we divide by the new exponent. What is 3x to the 3/2 over 3/2? 2x to the 3/2, right? Multiply by the reciprocal. 2 over 3 times 3x to the 3/2. You can see the 3's will cancel. We end up with 2x to the 3/2. Evaluated 1 to 2. What is 2 to the third? 8 square root. 2 roots of 2 times 2. 4 roots of 2. Minus, what is 1 to the third? Square root. 1 times 2. So 4 roots of 2 minus 2. What's the antiderivative of x to the third? Watch how quickly we can... Think about how long that problem would take you. X to the fourth over 4 minus third over 3 plus x squared minus... Ooh, let's see how that happened. So that was 3x to the 0, and you raise the exponent by 1. So that would be 3x to the 1 over 1, or just 3x. So if you have a constant, you just attach an x. Evaluate it at 1 and 0. We know what the 0 comes out to be, don't we? So let's just do the 1. It looks like we have over 4, right? And then you're going to have over 3, so let's write it all over 12. 3 twelfths minus 4 twelfths plus 12 twelfths minus 36 twelfths. Negative 1 plus 12 is 11. 11 minus 36. Ooh. Oh. After this, we would then subtract 0. So that would be after we did all these 4, then we would subtract 0. Take out your calculator so you can see what happened, everybody. Why might I be curious about this answer? Because it's negative. Very good. So I go back to my calculator. Let's look at it. X to the third minus x squared plus 2x minus 3. And we are going to calculate number 7. We can do the definite integral now. And we evaluate it from 0 to 1. What do you notice about the area? It is, if it's below the x-axis, it's counted as negative area. If it's below the x-axis, it's counted as negative area. So is it okay? Yes. It's just fine. Okay, we do 2 more. Antiderivative of sine of x. I had you guys do this problem earlier. I had you guys do this problem earlier in an assignment. You did the antiderivative. I'm sorry, you did the area of sine of x bounded between 0 and pi. You came up with 2.01 when we did 100 rectangles. Okay, so let's do this. Let's plug in pi. What's the cosine of pi? -1. Who was your trig teacher last year? Honestly. Yes, we're in radians. Minus. Okay? What is the cosine of 0? 1. So, minus the -1. What is -1? 1. Minus the -1 plus 1 is 2. And we do one more. 2 over x squared, okay? F of x is 2x to the -2, so that means big F of x is equal to (2x to the -1 over -1, or 2 over x. Oops, sorry, thank you. -2 over x. So, we have -2 over x, and we're going to evaluate that from 1 to 5. Question? I put 5 into it, so I get -2 over 5. And then you're going to subtract whatever we get when we plug in 1. So we have -2 over 1. So, as Larry said, we'll do -2 over 5, and we'll add 10 over 5, and we get 8/5. That's pretty sweet, isn't it? So, see this right here? Next page. It says at the top, Unit 5.3 worksheet, Fundamental Theorem of Calculus. Okay? That's all you need to do. Rip that out. Go to work.